Hello, everybody. Welcome back to the show. This is the Science Dispatch Podcast. I'm Cameron English, your host as always, joined by Dr. Chuck Dinnerstein, Director of Medicine at the American Council on Science and Health. Chuck, what is going on?
Not a blessed thing. It's a real summer day on the East Coast, which means it's hot and humid.
Beautiful. We love hot. We love humid. It's good for your mental state. You're in a better mood.
It's more of a sauna than a tandoori oven. So.
There you go. Things could be worse. Let's just put it that way. And let's move on to our story. This is beyond our normal thresholds, beyond our normal limits. Chuck, typically we're dealing with public health or medicine or something along those lines. But rocket fuel is where we're at today, courtesy of our colleague, Dr. Josh Bloom, Director of Chemical Sciences at ACSH. Articles called "The Perfect Rocket Fuel: No Fires, No Chemicals, Just Energy." It sounds like the marketing slogan for an energy drink. Nevertheless, it's not about energy drinks. There was a study published in Nature recently where they came up with what seems to be, based on Josh's description, the ideal source of energy because it burns very cleanly because there's no carbon in it. And it doesn't explode, apparently. It's just pure energy, which is, I guess, sounds like the holy grail. So let me read this introduction, and then you're closer to chemistry than I am as a doctor, so I think you know a little bit more. So maybe...
Well, I do have a bachelor's degree in chemistry along with psychology, but I would have to say probably I was stronger in the psychology end than in the chemistry end, but we're going to find out today.
Very good.
Whether any of those 4 years of undergraduate education paid off.
Okay, maybe we can do a dive into the psychology of these various chemicals. Okay, Josh writes, hexanitrogen is a newly synthesized molecule composed entirely of nitrogen atoms, making it the first known neutral polynitrogen, other than N2. It stores a large amount of energy in its strained bonds and decomposes cleanly into nitrogen gas, offering potential as a high-energy, non-polluting propellant, though it's extremely unstable at room temperature. This, of course, remains a major limitation. This plus other explosive trivia. Get the pun, everyone? Okay, Chuck, maybe just a very simple introduction. I don't mean to, hit you with a pop quiz about physical chemistry.
Well, that's okay because I'm not going to pass that.
Very good.
At all. So the chemical structure of this is three nitrogens connected by double bonds. And as Josh tries to write in the piece, these bondings that they've created for short periods in the lab under normal room temperature-like conditions are extremely strained, which another way of saying is that they're very energetic and they want to be something else. And by being able to constrain the molecule in this configuration for some time, they can direct the release of that energy, hopefully in terms of a rocket through a nozzle to provide that propulsion for a rocket. Now, why it's important is because we've been sending flaming objects into space for 50 plus years at this point. And while we used to be doing 1 or 2 or 3 or 4 a year, rockets are going up on a very regular basis in order to serve a increasingly crowded space full of GPS satellites, spy satellites, communication equipment, and various experimental gear that we've decided to pop up into space. In fact, you'll find a wealth of articles on the net talking about space trash and the trash that's either tumbling down into the atmosphere over time, or that has the risk of colliding as we create our kind of artificial Van Allen belt here in the 50 to 100 mile area that we call early space, maybe. In any case, the 6-nitrogen, the hexanitrogen, burns cleanly. It doesn't result in any formation of carbon dioxide because it doesn't actually have any carbon within it. And so that's what I think Josh is pointing to as making an important contribution. As he points out, the difficulty with this is that it is extremely unstable. It has a half-life of something on the order of 0.3 seconds at room temperature, but as with all chemical reactions, as you lower the temperature, you can slow the speed of the reaction. And so when it's cooled with liquid nitrogen, its half-life can reach out to over 100 years, which is neither here nor there. But certainly if we cool it sufficiently, which is something that is often done with our rockets today, it has the possibility of serving as a clean rocket fuel, since nuclear thrusters are yet to appear to take their place. And I think that Josh was kind of presenting this as an interesting moment in chemistry, which in fact it is.
And in fact, one of the experts quoted in the story, one of the stories that Josh quotes, says that this is probably Nobel Prize worthy. That's how significant a discovery it is. You were alluding to this. It sounds like there's a long way to go before this is commercialized in any meaningful sense. You got to learn how to mass produce the stuff and do it without blowing everyone to smithereens. Then you got to freeze a bunch of it, figure out how to transport. There's all of these different steps in actually creating a supply chain for it. But nonetheless, this seems to be a big first hurdle that they have overcome. Is that fair?
Right. It's absolutely fair to say. And I think that, the fact that there's a process from bench to rocket, so to speak, is worth noting, because there's a lot of things that come out of the laboratory that have to make that particular journey. More common, say, than rocket fuel would be pharmaceuticals. And there's a long way from a chemical that works in the laboratory to the point that you can show that it works for humans, and that you can scale its manufacture up to the point that it becomes a reasonably inexpensive material to use. So there's some echoes in there of what's involved in going from the lab to some, to common use.
What I wonder is if it would have application beyond launching rockets into space. Not that that's not significant. That's pretty cool. But, for air travel, maybe for, jet-powered airplanes, could this work? I wonder. I don't know if you know the answer to that. I'm just kind of thinking out loud.
I don't know the answer to that. On the other hand, I would think that it would be difficult to use in a plane, because just the additional weight of carrying the coolant might make the range of the airplane somewhat problematic. It's interesting because when you talk about the energy density of fuels, the fossil fuels are among the most energy dense fuels that we have, given their weight. And while you can talk about using electric systems, batteries while they may be renewable, are far heavier in terms of the energy that they might provide at any given moment in time. That's why we're not going to see a lot of electric airplanes for a while, because I guess you won't be able to carry any baggage once you have the batteries on board to do that. But we'll see.
So very cool stuff. It's, I guess, theoretical is the wrong word, because they've actually produced something here in the laboratory. They actually synthesized this chemical, which is pretty cool.
I think one of the nice things about this is that Josh makes this kind of chemistry accessible and palatable to a larger audience, and I think that's a real tribute to his understanding and being a chemist to do that, because that is not an easy lift.
Yeah, here's the bottom line, as Josh puts it. He says, this discovery has the potential to be a game changer in the world of rocket propulsion, although there are still issues to solve. Probably the best way to put it. And then he quotes another expert who says whether this has any application or not remains to be seen. Okay, so long way to go. Don't get your hopes up. You're still still highly dependent on fossil fuels for energy to any significant extent. Okay, so once again, the article is called "The Perfect Rocket Fuel: No Fires, No Chemicals, Just Energy" by Dr. Josh Bloom. That's on our website, acsh.org. When you're there, click on the subscribe tab. Give us your email address. We'll send you the stories that we publish. The ones you read are usually the ones we talk about. Visit us on X. It's at acsh.org. We're on YouTube and Instagram as well. It's called Matter of Facts, which is hosted by our colleague Anna Dolosky. Short little explainer videos and infographics tackling those burning science and health questions that everybody has. Go check them out, and you'll be a little bit smarter as a result. And with that, we're out of here. Thank you so much for joining us.